Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to derive an expression for the power spectral density of Manchester format. Let us start by looking into how a Manchester format is represented. In the Manchester format, a symbol 1 is represented by transmitting a doublet pulse of amplitude plus A and duration 1 TB, whereas symbol 0 is represented by transmitting a doublet pulse of amplitude minus A and duration 1 TB. The representation of symbol 1 and symbol 0 are shown in the figure 1 and figure 2 here. Let us start by writing an expression for the power spectral density of a discrete PAM signal x of t, and it is given by Sx of f equal to 1 divided by Tb magnitude square of V of f summation n varying from minus infinity to plus infinity Ra of n into exponential of minus j2 pi n f capital T, where Tb is the bit duration, V of f is the Fourier transform of the basic pulse V of t, and Ra of n is the autocorrelation function. Let us start with the derivation for the power spectral density now. We start by saying, suppose the zeros and ones of a random binary sequence occur with equal probability. Then the probability of occurrence of symbol 0, which is the probability of ak taking on the value minus a, is equal to the probability of occurrence of symbol 1, which is the probability of ak equal to plus a, is equal to 1 divided by 2. With that, let us now go on and solve for the autocorrelation function Ra of n. We should note the autocorrelation function is given by expectation on ak into a of k minus n. Just like what we have done for the polar format, we will once again solve this for n equal to 0 and not equal to 0. I'll start with n equal to 0 first. So, for n equal to 0, expectation of ak and a of k minus n reduces to expectation on ak square. So, this is equal to the first amplitude, which is minus a whole square, into probability of the same, which is probability that ak equal to minus a, plus the second amplitude, which is plus a square, multiplied by probability of the same, which is p of ak equal to plus a. This is equal to minus a whole square multiplied by 1 by 2 plus a whole square multiplied by 1 by 2. So, this reduces to a square. Then we move on for n not equal to 0. So, the product ak and a of k minus n has 4 possibilities, and this is shown in the table here. This is a simple 2 combination table which starts with 0 0 and ends with 1 1. Wherever there is a 0, you put a minus a, and wherever there is a 1, you put a plus a. So, in the product column, you simply multiply these values. So, it is minus a and minus a equal to plus a square, minus a into plus a is minus a square, plus a into minus a is minus a square again, and lastly plus a into plus a is plus a square. So, for n not equal to 0, we have 4 possibilities for the product ak and ak minus n. We then go on and say, assuming that the successive symbols in the binary sequence are statistically independent, these 4 product values occur with equal probability, which is 1 divided by 4 each. So, the autocorrelation for n not equal to 0 is given by expectation on ak into a of k minus n, which is equal to, you can look at this part here, we have 2 plus a squares and 2 minus a squares. So, I will write it as 2 multiplied by the amplitude, which is minus a square, multiplied by the probability of each of them, which is 1 divided by 4, plus we have 2 plus a squares, therefore, it would be 2 multiplied by plus a square multiplied by 1 by 4. This will result in a 0. Therefore, the autocorrelation function can now be expressed as Ra of n is equal to plus a square for n equal to 0 and 0 for n not equal to 0. Well, with that we have completed the computation of Ra of n part. Let us now move on to find V of f part. The basic pulse V of t for the Manchester format consists of a doublet pulse of amplitude 1 and duration 1 TB. This was shown at the beginning of the derivation here. This you see is symbol 1, which is a doublet pulse. This is a symbol 0, again a doublet pulse, but the amplitude is minus a. So, the Fourier transform of this doublet pulse is given by V of f equal to j TB sinc of f TB divided by 2 multiplied by sine of pi f TB divided by 2. Now, we will substitute equation 5, which is for V of f, and equation 4, which is RA of n, back into the equation for the power spectral density, and let us now simplify and find a final expression. Equation 6 is once again the same equation as that of the power spectral density I wrote at the beginning of the derivation, and let us start substituting now. Equation 5 is for V of f. This is magnitude square of V of f, though I have shown it here, multiplied by summation RA of n into exponential of minus j2 pi n f capital T. I'll square it out. There is a 1 by TB here, there is a TB and there is a square here. So, what remains here is TB. Then we have j square, but j square is minus 1, but then we have the magnitude here, so it would become plus 1. So, this part reduces to plus TB. Then we have sinc square of FTB by 2 followed by sine square of pi FTB divided by 2. As per the equation 4, which is for the RA of n, we have for n equal to 0 as a square and for n not equal to 0, 0. So, let me now split the RA of n into two parts here for n equal to 0 and not equal to 0. So, it is written as RA of 0 plus summation n varying from minus infinity to plus infinity, but not equal to 0 RA of n. Then we have the exponential part retained as it is. Let us now multiply the exponential part into the components inside the bracket here, but this part is for n equal to 0. So, exponential of 0 is equal to 1. So, this term is retained as it is. Then for the second term n not equal to 0, so I will keep the exponential part as it is. Let us now substitute the values for RA of n. For n equal to 0, that is RA of 0 is equal to plus a square, and for n not equal to 0, it is equal to 0. So, let us now simplify this part. So, this will be Sx of f equal to a square TB sinc square f TB by 2 followed by sine square of pi f TB divided by 2. This is the final expression for the power spectral density of the Manchester format. Before I end this video, I would like to show the normalized form of this equation 7, which is plotted here. We are looking for the Manchester format, and the Manchester format is shown here. So, this is the normalized part of the power spectral density plot for the Manchester format. Right. With that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.